Today, CITA is welcoming Anna Rosen from University of California, Santa Cruz, where she is a graduate student finalizing the final phase of her PhD. There she's working with Mark Krumholtz and Enrico Ramirez-Ruiz. She's a former graduate of UC Berkeley. And she's been on a long tour of throughout the Northeast. And they're one stop in Canada, so we're very glad to have her here.
Yeah.
Very happy to have her here. Go ahead.
Great, thank you. Yeah, thanks. This is my second time in Canada, so it's great to come by and experience the cold weather. Yeah, so I want to talk about what I've done for the last several years, or many years, and my PhD and work that I've done with Mark Krumholtz and Enrico Ramirez-Ruiz. And a lot of my PhD work has really studied the birth of massive stars and also the dynamics of the gas that surrounds massive star clusters to get a better idea of how stellar feedback can affect the formation of stars. And so my work is really focused on massive stars, and we know that massive stars are quite rare. So if you just look at a Krupa IMF, for example, and you integrate over the massive star population, so stars, let's say 10 solar masses and above, they really only account for 1% of the stars by number. However, if you take into account the energy output, so the radiation energy output that they give, and you integrate that total energy output over the stellar population, so let's say a newborn young stellar population, you find that they control 97% of the stellar radiation energy. So they really are the ones that dominate the energy budgets of like the Milky Way and other star-forming galaxies. So in a way, you can also think that massive stars represent the 1% of the universe. And because of that, they're very destructive. Because they give out these really high radiation fields. They also give out strong stellar winds, fast stellar winds, and then end their lives in supernovae explosions. And so to just give you an idea of how these different modes of feedback affect the dynamics of gas that they form out of, I'm showing 30 Doradus, which is a giant H2 region in the LMC. And this composite image kind of gives you a nice idea of how feedback affects the surroundings. So here, the cool gas, so the yellow shows the H-alpha emission, so basically the absorption of the stellar radiation field, so the pressure associated with that. Also, dust is the primary absorber for the direct radiation field, and so when the dust absorbs the radiation, it's going to heat up and it's going to re-emit, and you get this dust reprocess radiation field. And then also these stars have very strong fast stellar winds. And when the winds are launched from their surfaces, they're going to shock heat with the surrounding ISM and also collide with other winds and generate hot gas that's millions of degrees Kelvin that we see in X-rays. And you can see that here with the blue gas, with the blue emission from the X-rays. And then that hot gas can actually push on the surroundings. And so feedback actually affects the star formation process on small scales all the way up to large scales. So from small scales, the size scales of stars, for example, all the way up to galaxies. And so for individual stars, feedback can be very important during their formation as they're still actively accreting. So for example, massive stars will attain their main sequence luminosities while they are actively accreting. This gives you really high radiation pressure that might be able to halt the accretion flow into the star. Likewise, since they can attain their main sequence luminosities while they're accreting, they also get their main sequence stellar winds. And so the effect of stellar winds can actually shock heat the infalling gas and also ablate the accretion disk. They also have these magnetically launched collimated outflows that are launched along the polar directions of the star, and this can also evacuate material that's trying to fall into the star. And so the combined effect of these feedback processes can actually limit accretion into the star and set an upper mass limit to the IMF. It can also affect the distribution of stellar masses. And that's going to have important implications for the type of supernovae that go off. And so a lot of the heavy elements are created in these supernovae explosions. And so ultimately, the processes that affect the formation of these stars can then limit the upper mass limit of the IMF, which can then affect the chemical evolution of the universe because most of the elements are created in the resulting supernovae explosions. Something that I did early on was to try to understand what sets the initial rotation rates of massive stars. And it turns out that massive stars are born as fast rotators. And so, and this project was, we just wanted to see if massive stars spun down like their low mass counterparts. If the star has a magnetic field interacting with the surrounding accretion disk, you can impart torques on the star and spin it down. And so here I'm just showing the initial rotation rate of stars as a function of mass, and also showing the radius of these stars as a function of mass. And it turns out that massive stars are really hard to spin down because rather than being big and fluffy like these low mass stars, they actually reach the main sequence very quickly, and so they have high inertia, so it's hard to spin them down. And the effect of being fast rotators will actually enhance feedback from these stars by increasing their luminosities and their mass loss rates. So now on medium scale, so the size scale of clusters and GMCs, here's a picture of NGC 3603, which is kind of like a superstar cluster in our own Milky Way. And you can see that the integrated effect of feedback actually can launch cluster winds or eject a lot of the gas in these clusters that could otherwise form stars. And so this leads to low star formation efficiencies from GMCs and can also lead to the eventual disruption of these clouds. And then on large scales, you really need to include feedback to explain the low star formation rates observed in galaxies. So this, for example, shows some simulations by Gertz et al., where they ran a series of galaxy formation simulations and varied the type of feedback that they included. And they found that if you properly inject energy momentum from stellar winds, supernovae, and radiation, you can actually match the observed cosmological value of star formation rates over cosmic time. And then also, furthermore, the integrated effect of feedback can actually launch galactic scale outflows from these galaxies. And that can also explain why you have these low star formation rates in galaxies, because you're just like on the cluster scale and now on the galaxy scale, you're ejecting material that could otherwise be turned into stars. So my PhD has focused on the small and medium scales, and so I'm going to go over the small scales first. And I really focused on radiation pressure. And you could think of the formation of massive stars as a combination or a competition between gravity of the infalling gas, but also the radiation pressure from the intense radiation field from these stars. And so for radiation pressure and massive star formation, there's really two components. The first is the direct radiation pressure. So that's due to the first absorption. So this is kind of denoted by this factor of 1 here. That's due to the first absorption of the stellar radiation field by dust, and then that dust is going to heat up and then and re-emit, and you could get multiple scatterings that way. And so that's just this F-trap factor. So it's kind of like how much is the radiation pressure enhanced by the dust. And then you can compare both forces. So the radiative force, compare it to the gravity force, just take the ratio, and which is known as the Eddington factor or Eddington ratio. And basically, regions where F Eddington is greater than 1 means that your radiation pressure dominated. So radiation pressure should halt or overcome the gravity of the infalling gas and actually turn over the accretion flow. And so if you assume simple spherical accretion onto these stars, it turns out that radiation will halt isotropic accretion when the star is about 20 solar masses. But if you actually look at stars, we find that there's a lot more stars more massive than this, and so so that means that you can't have this simple isotropic accretion scenario. So for example, some of the most massive stars that have been observed, and this happened very recently. So Cruther looked at R136, which is a superstar cluster or a very massive star cluster in the LMC. So it actually powers the Doradus that I showed before. And by looking at the UV spectroscopy with Hubble, they found several stars that probably had solar masses, greater than 300 solar masses when they were born. And so I'm just showing that here. And so, the question is, how do these very massive stars form? And so to study this, because massive stars are very rare. The star-forming environments that they form out of are also very rare and very obscured. We really need to use multidimensional radiation hydrodynamic simulations. We need multidimensional because the accretion flow must be anisotropic. And then also we have to include radiation pressure because that is a very important feedback mechanism in these types of physical processes. And so now the nice thing is that considering the fact that the star-forming cores that these stars form out of actually do rotate, they do have angular momentum, this leads to a natural way to get anisotropic accretion onto these stars. So for example, here is just showing a number of cores, and you see beta is just the rotational energy divided by the gravitational binding energy of the cores. And you see they're slow rotators. And so as the core collapses, you're going to build up an accretion disk around the star, a dense accretion disk, as shown here, that can funnel material to the star, and the radiation can just escape along the poles. And so the idea is kind of simple. So this is known as the flashlight effect. The disk shields the radiation field. You have this high ram pressure flow that can accrete onto the star. The radiation can escape, and then the star can grow. And so there's been a number of multidimensional simulations that's been done to study this effect. And so I'll talk about the first few 3D simulations. So the first 3D simulation with radiation pressure was done by Krumholtz et al. In 2009. And they used the Orion adaptive mesh refinement code, and you can have an arbitrary number of stars form, and they interact with the accretion disk and so on. And they find that the star can grow two ways. The first is that you can accrete material to the star through an accretion disk, as shown here. But also the radiation pressure bubbles that expand above and below the star later become unstable, and you get these Rayleigh-Taylor instabilities that can then deliver material. You get these dense fingers that can actually penetrate through the radiation pressure dominated bubbles and deliver a lot of mass that way. Now, one limitation that they had was that they only included the indirect radiation pressure, so the Desser process radiation pressure. And they basically, the way that they modeled the stellar radiation field was that they just dumped the energy, the stellar radiation energy, near the star, and then the energy was just absorbed throughout. A couple years later, Kuiper et al. Did some nice 3D simulations also, and they included both the direct and the indirect radiation fields, and their geometry was a bit more limited. So here, the stars can move. You can refine in areas that you care about. Whereas in Kuiper's setup, the star is held fixed at a spherical domain. And so you have better resolution as you get closer to the star, but poorer resolution away from the star. But since it's a spherical domain, you can easily model the direct radiation field because they use a ray tracer where you shoot rays through the domain from the star. And they're just radial rays going through a radial domain. And so they find that you don't get these instabilities, these Rayleigh-Taylor instabilities. Instead, the star is only fed through disk accretion alone. And so they suggest that inclusion of the direct radiation pressure actually inhibits the growth of these instabilities. But both of these simulations had their pros and cons. For example, Krumholtz et al. Had the geometry was very flexible. The stars could move and everything. Whereas Kuiper et al., by holding the star fixed, you might suppress instabilities that could later develop. And so really a lot of my work was to combine both, the pros of both types of simulations to test out this problem. And so what I worked on was to actually treat stellar radiation better in these types of AMR simulations. And so to do that, I added adaptive ray tracing to the Orion AMR code, the same code that was used in the 2009 simulations. And then, and the way that this works is we shoot rays from the star, and then as these rays move away from the star, they can actually split. And the way that we decide to split the rays is just based on conservation of solid angles. So you have more sampling away from the star than close to it. And the including adaptivity for these rays actually reduces the cost by a lot. And now as these rays propagate through the domain, they will interact with the gas. And we just solved the radiative transfer equation directly along these rays. And so we can calculate how much of the energy and momentum is absorbed from the radiation field and transferred to the destined gas. Here's just kind of a proof of concept showing if you turn off absorption that the flux falls off as 1 over r squared, as it should. And so just in short, my PhD a lot of it was to add this multi-frequency adaptive ray tracing and an adaptive grid-based code, which also includes adaptive time stepping. And then a lot of effort was spent on the parallel communication of rays to different processors. And so I developed a highly optimized adaptive asynchronous parallel ray communication algorithm. So a lot of adaptivity. And as Mark said, if it were any more adaptive, it would be self-aware. So including the adaptive ray tracing allows us to model the direct radiation field. We still have the flux limited diffusion, which is a moment method that models the dust for process radiation field. And so I coupled those two together so that we have a full-on hybrid radiation scheme in Orion that models both the direct and indirect radiation, the radiative heating and pressure from both of these types of radiation fields. And so here is also just another proof of concept test where we have a dense cloud illuminated by 2 sun-like stars. And we let the cloud absorb energy and momentum from the stellar radiation fields. And you'll notice that it causes the gas to heat up and expand, and also causes the cloud to move as more and more energy and momentum is absorbed. So after all that, I wanted to revisit this question: how do these very massive stars form? Is it through disk accretion alone, or do we still expect to see these Rayleigh-Taylor instabilities that can deliver a significant amount of mass to the star? And so I did a repeat or a similar simulation as like the ones I showed before. So this is just for an idealized laminar core. It has no turbulence. And the core is 150 solar masses. It has a surface density of 1 gram per centimeter squared. And this is based off observations of star-forming cores. We give it a net rotation. It's slowly rotating so that we expect to form an accretion disk. And the maximum resolution is 20 AU. And so the top panels here are just the whole core. You'll see collapsing. And the bottom panels here are zoom-ins. And this shows the YZ plane. And this shows the XY plane where you'll see an accretion disk form because we give the rotation axis is along the Z axis. And so every time we make a star, I'm just over plotting the stars that have 0.1 solar masses or above. So I'll play that. So we make a star at the center, and then the radiation pressure starts to evacuate these bubbles, both above and below the star. We get a lot of fragmentation in the accretion disk, and that's just due to the magnetic field, or no magnetic fields in the simulation. That's due to the massive star interacting with, like you have gravitational torques induced in the disk that can then fragment. And so I'll play that one more time. And so you can also notice that even though we include the direct radiation pressure, we still get the bubble shells still become unstable. And we can deliver a significant amount of mass to the stars, to the stars themselves. And so this is a 3D, this is a volume rendering of a snapshot from the end of that simulation. And you can see that basically the entirety of the bubble shells become unstable. And so that these instabilities are actually quite significant at delivering mass to the star. And one way to kind of understand why we still get these instabilities even when we include the direct radiation pressure is that you can think that this is not a symmetric system like that was simulated before. The star is moving in this thick accretion disk. Parts of the accretion disk can actually shield the radiation field. As you can see here, this shows the acceleration vectors for both the direct and the diffuse radiation fields, or radiation pressures. And you see that the absorption of the direct radiation field is not uniform across the bubble shells. And not only that, based on the flaring of the accretion disk, that can weaken the radiation pressure along certain regions of the bubble shells. And this asymmetric absorption can actually feed into or lead to the perturbations that can eventually grow into really Taylor instabilities.
But do you see much in the way of feeding of the star from the polar regions?
Sorry?
Practice, you don't see much feeding of the star.
No, not always. It's mostly just the edges, because here, yeah, here you feel a much stronger force. It's mostly just the edges that bring a lot of material down.
Those polar regions don't exist, right? Because there's a protostellar outflow.
Yeah. So also once you have protostellar outflows, those polar regions will go away.
There's material flowing out as well from the star.
Yeah. Well, yeah. So this doesn't have protostellar outflows, and the effect of protostellar outflows will actually evacuate material above and below the star. So this material will be evacuated away, and then it will also increase the opening angles of those outflows will increase with time.
Have you done any cross comparisons with the Princeton code? Because
With Athena?
you think that was getting different results than
Oh, that was for, yeah, with the VET. No, but we're adding VET to Orion right now. Yeah, so we'll likely repeat this again. Yeah. Yeah, so Berkeley, a lot of my collaborators have been working with like Jim Stone and Eve Ostreicher, and I think we're gonna do some comparison runs, but they're adding VET to Orion now. Yeah. No, I mean, it would be interesting. Is it a numerics thing? Okay, so of course, at around the same time I was writing that paper up, this paper came out, which is very similar to what I did. So this is some work by Klassen et al. And they added a similar hybrid radiation scheme to the Flash AMR code and simulated the formation of massive stars, like I did. And something interesting to note, which at first was kind of scary, was that they got completely different results. Their bubble shells do not become unstable at all. And so at first, like I said, that was kind of scary that it was totally different from our results, but then it got me to really think about why do we see this and they don't. And so I just think hard about RT instabilities and how they grow. And if you just look at classical RT instability theory, the idea is that if you have a perturbation, the perturbation will grow exponentially with time, where the growth rate depends on the size scale of the perturbation. So the smallest modes will grow the fastest. And so to be able to see the growth of these modes, you have to be able to resolve them. And so I'm just comparing Klassen's work with my work. And here you can see they don't refine their bubble shells like we do. They basically have maybe the cell sizes at the bubble shells are probably like 160 AU. Whereas for us, we have the cells along the region, or the cells along the shells are about 20 to 40 AU. So we're at least a factor of 4 better resolution. And that's just because we have different refinement criteria. And so we refine on the genes density, just like Klassen, but we also refine on the change in the radiation energy gradient. And so I'm just showing that here, the radiation energy density. And so the gradient is going to be sharp when you're going from optically thin to optically thick regions. So from low density material to high density. And that's why the majority of our bubble shells are refined. And so, this type of analysis kind of suggests that maybe the reason why they didn't see these instabilities was because they just weren't able to resolve the small perturbations that can then grow. So to test this out, I did a repeat of the simulation, but with lower resolution, and I did not refine on the radiation energy density. So this will cause the bubble shells to not be refined, like I did before. And so, of course, again, you see that the bubbles expand away from the star. And they're much more stable now. They only start to become unstable later. So for example, in the high resolution run, the bubble shells start to become unstable when the star is about 25 solar masses. And in this run, they only start to become unstable when the star is 40 solar masses.
So are you confident that they wouldn't have become unstable earlier if you had to do it higher resolution?
Maybe. I haven't calculated that yet. Yeah. They might have, yeah. Oops. Yeah, so, and then you can also kind of see why, you can correlate the locations where the bubble, or where the shells start to become unstable with the flaring of the accretion dust. So you're feeling a weaker force and it's coming, and then it starts to move down towards the star. And so we think the differences in our interpretation of the result is just basically a resolution effect.
You said that the development of the instability was good.
That what?
Or the development of the instability was good for feeding mass.
Yeah.
So at the given time in the simulation, when you have the refinement, is the central star more massive at a given time because it's being fed by the instability?
Oh, I mean, I think so. The instability. So, if you look here, if we compare, so here, because their bubble shells are never become unstable, their material is just going to be evacuated away from the star. For us, we're able to deliver material to the accretion dust through these instabilities. So I didn't calculate the rate, like how much mass is added, but a significant amount of mass is added to the accretion disk through these instabilities.
Well, they get up to 40 solar masses at 20,000 years.
Oh,
What did you get?
so they have denser cores, or not denser, but they have 200 solar mass cores, so it is denser.
It's not exactly.
It's not exactly the same, yeah.
Oh, but you simulated low res and
Oh, yeah, I didn't compare that.
so you could do that.
I could do that for their 200, but
No, you could compare yours at low res with yours at.
oh, yeah. The only difference though is that I get less fragmentation. So at the point, yeah, I could compare that. But the thing too is that with the high resolution simulation, I have a lot more fragmentation than I do here. So there's a lot more mass in the companions in the other run. Yeah, so that also affects, right?
Go somewhere else.
It goes somewhere else, yeah. I mean, I could do it for just total stellar mass. Yeah, actually, that's something good to look at. Oops, okay. So after all that, that kind of was like an idealized experiment because we all know that star-forming cores are actually turbulent. And in fact, since they're turbulent, the turbulent itself should actually act as the initial seeds for these instabilities. And so I did another similar simulation, but instead of giving the core a net rotation, I instead seeded it with supersonic turbulence. And I just added that to the velocity field. So that's going to feed into the density distribution of the cores. And so the setup is exactly the same as before. So you full core on top, zoom in on the bottom, and this shows the YZ plane and the XY plane. And so again, we form a star at the center. Radiation pressure tries to blow these bubbles, blow material away from the star. But you have these dense filaments that can actually crush these bubbles and deliver a lot of material to the star. But also here, if you look at top, you see that radiation pressure can still blow a lot of material away, but a lot of material is being fed to the star through these dense filaments. And also, the material becomes unstable. I'll show it one more time.
What Mach number is here?
I know it's slightly supersonic. I can't remember the Mach number, though. I'd have to... Yeah, it was I think it was like 1.4, 1.5. Yeah. Yeah, so basically what we're seeing here when we have initial turbulence is that a lot of the mass can be fed to the star through these dense filaments before a significant, a large accretion disk forms. And so the idea is just basically that you just need any type of asymmetric or anisotropic accretion flow to feed material to the star. And so here I'm just kind of showing So the top panel here shows the YZ plane, so where the bubbles are expanding outwards, and you see that early on these bubbles are crushed by the inflowing filaments. They're also hard to sustain because the star is being kicked around a lot because of the momentum that's being added to the star from the anisotropic accretion flow. Here, this kind of shows the formation of the accretion disk. We can only talk about the accretion disk outside the 80 AU accretion radius. But it's not until...
Does the formation of that accretion disk coincide with your expectations based on the angular momentum of the initial distribution?
I didn't calculate the net angular momentum of the core. So it could... That's something I should look at where it could be due to the net angular momentum, because the core should have some net angular momentum. However, it could also be due to like grid artifacts, so where it preferentially formed along the z direction. Yeah. I was talking to someone else, and he was like, "Oh, that probably formed because of it's really it's a numerical artifact. You kind of can introduce angular momentum when you have a grid-based AMR code." So here I'm just showing the pressure. This shows the ram pressure of the infalling material, and also the pink line here shows the direct radiation pressure. Then this is a sphere that's 1,000 AU from the star. And what I really want to note is this line here shows the mass-weighted infalling the mass-rated ram pressure of the infalling material, whereas this line here shows the spherically average ram pressure. And so most of this ram pressure is due to these dense infalling filaments onto the star. And if you only kind of look at the spherically average value, you find that at about 30 solar masses, it's much less. And so basically, to be able to feed material to these stars, you just need some dense infalling filaments that are like order of magnitude larger than the direct radiation pressure.
So this is ram pressure some
Like a sphere. Yeah, 1,000 AU from the star, yeah. And then towards the end, you kind of get this one-to-one comparison between the direct radiation pressure and the ram pressure. And I think that's mostly due to the accretion disk at this point. And so if I kept this running, I think we still would have gotten a lot more mass onto the star. And so after all that, did I solve all of massive star formation? And the answer is no. There's still a lot of things that are missing. So I really only included radiation pressure, but like I said before, there's more physics that's missing. So the first thing is the magnetic fields. I did not include magnetic fields with that. And that can reduce fragmentation in the disk and also the size of the accretion disk that forms. I also did not include outflows. That will could potentially make these Rayleigh Taylor instabilities less significant because they'll basically punch holes in the ISM, above and below the star and evacuate material that way. And then also, I did not include stellar winds. And so stellar winds can actually ablate the accretion disk over time. And so that can limit the accretion onto the star. But the nice thing is that radiation pressure is treated well. And future work that I plan on doing is to include all of these effects. Because I think for us to really have an idea to understand how accretion can be limited by stellar feedback, you have to include all these different components.
Principle, this code produce a H2 region, you got the right density.
So we have people working on ionization right now. So the nice thing with the adaptive ray tracing is that you can do it for any type of physics. So I did it with the direct radiation field, so just dust opacities, and now we have some people that have been working on getting photoionization in there.
In some regimes, there will be obviously some thermal pressure.
Yeah.
And do you give us a sense of where and when that would be important?
Low metallicity.
I'm sorry?
Low metallicity. And also when, so for example.
But eventually, at some rate stage, you must be some control, right?
Yes, actually, I think, because if you have 10,000 Kelvin gas, then you're likely not to have, there's not going to be any dust that will survive in that. And then that will definitely be important. Yeah. So that would probably be later times, yeah. Did that answer your question?
Well, I mean, it just looks based on your simulation that nothing's turning this process off, right? So
Not yet, no.
it keeps on building and eating and eating.
Yeah.
Either you run out of like a cloud or something else has to happen.
Yeah. So that's why we need to include other physics. And you're right. Like we also need to include photoionization because that will be more important later. Yeah, and we have someone. There's a postdoc now that's been using the direct radiation, and we'll be using the photoionization to see how that affects the formation of these stars. Because once you destroy the dust, then the direct radiation pressure is not that important, or I mean, it's not important at all. Then you're gonna be probably dominated more by the warm gas pressure or the hot gas pressure from the winds and so on.
It's not completely true because you still, if you photoionize the gas, you still transfer the momentum from the ionizing photons to the gas. And so even with zero dust, you still transfer the radiation.
Through photoionization, not through the dust. Yeah. So what I've done focuses more on the dust, the radiation pressure associated with the dust. Yeah. Okay. So that was my work on small scales. And now I've also wanted to talk about stellar feedback on medium scales. And so this is NGC 3603, like I showed before, and you see that the integrated effect of feedback from all these stars evacuated a lot of the gas from these stars, from this GMC. And this is gas that will not be turned into stars. And one thing, if feedback is very efficient and can eject a lot of gas over a very short time scale, you can actually disrupt young star clusters. And so I'll kind of give like a real life example of how you can disrupt these types of star clusters. This is probably also why I like these star clusters a lot. So this is me and my siblings, and that's me, I'm the cute one. And in the context of star clusters, if you're able to eject a lot of gas very quickly, so even if you start out as a bound cluster, you're bound by the gas and the stars. And so if you can eject the gas very quickly, such that the stars don't have enough time to adapt to become bound again, then the stars can just be dispersed into the field. And so for us, it took like a year, but for a star cluster, it'll probably take 1 or 2 crossing times if you can evacuate the material very quickly. And don't worry, we're fine. So this is given a lot of attention to trying to study how feedback affects the formation of star clusters. And the first thing, too, is to be able to understand how stellar feedback can lead to the disruption of star clusters is to also understand what feedback processes dominates the dynamics of the surrounding H2 regions. And so this shows some work from my collaborator, Laura Lopez, where she did a multi-wavelength study of 30 Doradus and to study the different pressure components associated with the direct radiation pressure, the dust for process radiation pressure, the warm gas pressure, and also the hot gas pressure associated with the feedback from winds. And one thing you'll notice is that the hot gas pressure associated with the shock heating of stellar winds is actually much lower than all the other pressure components. And then one of the questions is, why are stellar winds so unimportant? Because if you assume all the energy from the winds are retained within the bubble, you would expect this to be much higher. And then furthermore, the energy input by winds over a star's lifetime is actually comparable to the resulting supernova. So if we think supernovae are important, then winds should be important earlier on. And so the way that stellar winds inject energy into the surrounding cluster is you have a bunch of massive stars, and then the stellar winds will collide with the winds of nearby stars and also the ISM, and you shock heat this gas to millions of degrees Kelvin. And then that gas will adiabatically expand and fill the H2 region, and we'll see that emission from X-rays, as shown here for 30 Doradus. But if you take into account the total wind energy you expect to be injected over the cluster's time and compare that to the energy density of the hot gas, you find that you're actually missing a lot of the wind energy. So the total wind energy is much higher than the energy density in the hot gas. And so one of the questions that I wanted to answer was, where is the missing energy? Assuming that all the hot gas, or all the wind energy is thermalized and should be in this hot gas. And so to do this, I developed a model to basically consider different energy sinks or energy transfer mechanisms for the hot gas. And so our model just requires, we need to know the total energy input by the stars. So we need to know the spectral typing of all the massive stars in the H2 region or in the star cluster. And then because we assume that the hot gas fills the entirety of the H2 region, has a filling factor of 1, this makes it kind of like the most, we're being highly optimistic about how the hot gas can affect the dynamics of the gas that surrounds these H2 regions. We require X-ray observations to characterize the properties of the hot gas. And then also, we need to know the size of the H2 region and the expansion rate of the H2 region, so we require radio observations for that. And so these requirements led to 4 well-studied H2 regions in the LMC and the Milky Way. And from the X-ray observations, if you know the emissivity, then you can calculate what the number density of the hot gas must be, assuming a single component hot gas that fills the entirety of the H2 region. And you can calculate, just by knowing the X-ray luminosity, the size of the H2 region, the emissivity of the hot gas, what the number density of that is. And then from that, knowing the temperature and the gas density distribution of the hot gas, you can consider several different energy transfer mechanisms. And so to do this was using that information, I was able to calculate the energy loss rates or transfer rates, so this L-cooled, mechanical, and so on, from the hot gas properties. And so I took into account several properties. So the first is cooling, so just radiative cooling from the hot gas. Mechanical work on the dense shell. So if a lot of the wind energy can go into mechanical work, means it's pretty efficient. Thermal conduction. And so this is also, we assume like heat flux between the hot gas at the interface between the H2 region and the shell. And then also dust grains that could be mixed into the hot gas. And so that you can transfer energy through collisions. And eventually the dust will be sputtered and destroyed. But if you can continuously feed in dust, then that can take out a significant fraction of the energy. And so I'm just showing the example here for 30 Doradus. So just showing the energy, the fraction of the energy that can be accounted for with these different rates. And then the accounting part is we just add it up. The shaded region kind of just denotes the energy that we're missing in these H2 regions. And so I applied this analysis to all 4 H2 regions in our sample. The stars here just denote the spectral, or the temperature inferred from the X-ray observations from previous work, just to guide the eye. And you'll notice for Carina and NGC 3603, even under our most optimistic conditions, we're still missing a lot of the energy. So for example, our estimates for thermal conduction is probably too high because we neglect the effect of magnetic fields. If we have magnetic fields, that's going to suppress the heat flux. Now, for 30 Doradus, we get pretty close to the answer, whereas for M17, we highly overpredict. But that's likely because of our estimate for thermal conduction. Oops. There. And so this is just corresponding to the observed or temperature values for these H2 regions. I'm just kind of giving you an idea of how these different components contribute. And so you look at Carina and NGC 3603, only a few % of the wind energy is actually going into doing work on the ISM, the surrounding ISM. And then, of course, you see that dust under our most optimistic conditions can actually remove a lot of the energy. And same with conduction, but that's probably overestimate. But one thing to notice, for M17, which is the youngest H2 region in our sample, it's about 1 megayear old, about 40% of the wind energy goes into pushing on the ISM, on the surrounding shell. And so this suggests that maybe early on feedback from winds is important, and then just becomes less important later. And so there's a couple other ways that that the energy can be lost. And this is first, so this first came from Harper, Clark, and Murray here, where if you have, you can actually lose hot gas if there's like holes in the shell. So because the sound speed of the hot gas is much greater than the expansion rate of the shell, you can lose, and if the H2 region has holes in it, then the hot gas can just escape. And so these simulations by Rogers and Pittard kind of show how, as time goes on, you can lose a lot more, you develop more and more holes in the shell, and so the feedback from these winds, or the hot gas from these winds, are more likely to escape later on. Another possibility, which is similar to like the laminar thermal conduction that I talked about, but this is actually turbulent thermal conduction, is that as the H2 region expands, you can develop these instabilities in the shells that can actually mix the cold and hot gas in even smaller scales. And if the size of these instabilities are small enough, then the effective magnetic field is not going to be that important. And so you can actually transfer a lot of energy this way. However, these types of mechanisms, in my previous model, are not really easy to calculate. And so we really need to look into doing more detailed 3D simulations of cluster formation with magnetic fields, dust, radiation pressure, and so on to really be able to pinpoint this down.
Given that these other mechanisms exist, are you surprised that you got so close?
Yeah, so the thing is, I think our value for thermal conduction is way too high because that's going to be highly suppressed with magnetic fields, and we know that these HE regions should be magnetized. So I think this is going to be really helpful with that. And then thing too is that this depends on the porosity of the shell, so we don't really know what those are, what that is. But I guess, yeah, it was good. But we also, the work on the shell only accounted for like 30 to just like 15%. So, yeah, I guess I think just because a couple of those mechanisms are kind of uncertain that it's hard to tell when you have upper limits. Yeah. Okay. So that work and other previous work suggests that feedback from stellar winds is probably not that important for young star clusters. And so some work by Mark and Chris was this idea of, for the very dense, massive star clusters, they tend to actually be radiation pressure dominated over being warm gas dominated by the photoionized gas. And this works for GMCs that have escape speeds greater than 10 kilometers per second, so greater than the sound speed of the warm gas. And so here, just the only thing to really pay attention to is this line here, where if you're above this line, you're radiation pressure dominated, so like direct radiation pressure dominated, rather than the warm gas dominated. And this is true for a number of star clusters, dense star clusters, and the Milky Way and other galaxies. And also, observations of GMCs find that the star formation efficiency per free fall time is quite low. It's varies between 1 and 10%. And also, these clouds are magnetized. So some work by Crutcher that measures Zeeman splitting for a number of molecular clouds and finds that the clouds that rich stars form in are magnetized, and so that can actually, the effect of the magnetic pressure can actually slow down collapse. And so, this could lead to low star formation efficiencies early on, and then later on feedback, so like from radiation pressure, can inhibit star formation later. And so I'm testing this out now. I'm using our hybrid radiation treatment to model the formation of massive star clusters. So star clusters that we expect to be radiation pressure dominated. And so I'll just show the early work now. I'm doing my MHD simulations of this. So we have that the cloud, the mass to flux ratio is about 2, which is in agreement with observations. And it also means that they're supercritical, so gravity is a little bit stronger than the magnetic pressure, so the cloud's going to collapse, but magnetic pressure is going to slow it down. And so my initial conditions are that the magnetic field is along the z directions, uniform along the z direction. Again, I see the cloud with turbulence, and so that's going to mix up the density structure of the gas. It's also going to change the density, or the magnetic field structure. The cloud is highly supersonic. It's virialized as alpha vir of 1. And yeah, so this is running now. So And instead, because we're not able to resolve individual stars, so instead of individual stars, I have little star clusters. So once we form stars, the stars represent these small star clusters, and then as they accrete material, we pull stars stochastically from an IMF, from a Krupa IMF. And so I'll show that now. So you see the turbulence gives you these dense filaments, and then interacting with the magnetic field, it kind of stretches it out. You get stars forming in the densest regions. I'll play it one more time. And it looks kind of spotty just because this cluster particles can actually merge if they get too close.
So this one, unlike the previous ones, is more of a uniform initial sphere of gas.
Yes, it's uniform, exactly. Which I was talking to someone about, what's the best, someone who studies molecular clouds. Yeah?
What type of turbulence generator do you use to assign the turbulence index that kicks it all?
We have a, well, okay, so you give it, we have it, I don't know the exact name for it, but we basically use Fourier transfers we do calculate the Fourier spectrum for a range of wave numbers. Yeah, and then we add that to so it's like a 3D perturbation cube that we add to the velocity structure. Yeah, so this follows a k to the -2 power spectrum. So that's like for supersonic turbulence. Okay, so just to kind of give you an idea of the early results right now. So here I'm showing the surface density and also the magnetic pressure, and you see the magnetic fields are enhanced in the densest regions, and that's also where the stars are forming. And so that's going to slow down the formation of the stars within this cluster. And so you can see early on, it takes a while for us to start forming stars. At about 1 free fall time, we get 2% star formation efficiency, so that's just the total stellar mass divided by the initial cloud mass. And now it's kind of ramping up. And so comparing this to Skinner and Oestreicher, where they also did a nice similar simulation, but they don't include magnetic pressure. They get higher at 1 free fall time. They get like a 20% star formation efficiency that ramps up. And so I still need to keep this running, but it'll be interesting to see how including magnetic pressure with the radiative feedback and the direct radiation pressure, they only include the IR radiation pressure, or the dust per process radiation field, to see how that will affect our star formation efficiency. And so this is the beginning of a suite of simulations that I want to do, or that I'm doing now. And so for the next few years, I want to look more into massive star cluster formation, but also how does feedback from these different modes of feedback really affect the formation of star clusters and affect the dynamics of gas that surround these star clusters. And so the first thing is to revisit this missing wind energy problem, but to do it with these really nice, highly detailed 3D numerical simulations. And so the work I talked about before kind of really helped motivate these next set of simulations, where we want to include feedback from radiation pressure, but also from stellar winds, and generate that hot gas and see how the energy from the hot gas is transferred to the ISM. And also to see, for example, test that idea, like, are stellar winds dynamically important during the early formation of these clusters and just become less important early on? And also, which energy sink mechanism dominates the stellar wind energy budget? And then furthermore, because we'll have the direct information about like the density and the temperature profiles, we can use that to make mock observations to compare to the actual observed H2 regions, where we do see this low X-ray emission. Now, stellar winds can also lead to the production of cosmic rays, and these have been getting a lot of attention lately for accelerating or for launching galactic scale winds. However, basically about a few percent of the wind energy, it's been shown, can explain the gamma ray emission, or the high energy or non-thermal emission of star-forming regions. And also some nice work that Laura Lopez has been doing is studying, she's been looking at the Fermi data for the LMC, and here I'm just showing the Fermi data for 30 Doradus. And you see that 30 Doradus is gamma ray bright, and that the gamma ray emission follows the star formation rates. So this is just showing, the contours show the H alpha emission. And so this suggests that these gamma rays are likely produced within 30 Doradus or within R136, meaning that the gamma rays are probably, or the cosmic rays, so you get this gamma ray emission by annihilation of cosmic ray protons, high energy cosmic ray protons. And before they will be annihilated by interacting with the dense gas, they can actually, by interacting with the magnetic fields in these star clusters or these H2 regions, they can scatter out the magnetic field lines and impart a lot of momentum to the surrounding gas. And so what I want to do is add cosmic ray diffusion to Orion, and it turns out it won't be too difficult just because we already have an isotropic diffusion solver, and so I can extend that to include anisotropic diffusion coupled to the magnetic field to model cosmic ray feedback and star formation and massive star cluster formation.
What's the gamma ray power of 30 Doradus compared with the estimated wind power?
So we haven't calculated that for 30 Doradus. Laura is still working on this right now, so I haven't gotten any numbers. This gamma ray emission shows the 2 to 300 GeV gamma rays, which comes from the GeV protons. But there has been some work way back when, and I mean not so much related to the gamma ray emission, but for the non-thermal emission for star clusters, and they suggest that a few percent of the wind energy can go into explaining the non-thermal emission.
You meant 2 to 300 MeV.
This is GeV. This is GeV. So protons account for 99% of the GeV cosmic rays, or sorry, 99% of the GeV cosmic rays are protons, and it's protons that are important dynamically, and it's the GeV protons that would be dynamically important. Yeah.
Sure. But you said 2 to 300 GeV gamma rays.
Yes, as measured by Fermi. That's just the combined emission from that. Did that answer your question?
This is a question, that's all.
Okay.
Thanks. Yeah.
Okay. That's the numbers Laura told me, 2 to 300 GeV. Okay. And so by studying cosmic ray feedback for the formation of massive star clusters, there's a couple of questions you can answer. The first is, how does cosmic ray pressure affect massive star cluster formation? And then also, something that will be very important for trying to understand cosmic ray feedback in galaxies is, what is the escape fraction of cosmic rays from star-forming regions? So not all of the cosmic rays are going to be annihilated, and some of them can escape and then impart momentum in even larger scales. And then all of this by studying these different feedback feedback mechanisms in much greater detail, and studying how these feedback methods or these feedback mechanisms affect star formation on the individual and also the cluster scale, can allow us to also develop better detailed subgrid models to be used in cosmological simulations. So I'll just leave this up here. So on small scales, I found that Rayleigh Taylor and gravitational instabilities can deliver a lot of material to the massive star. And then going on to medium scales, feedback from stellar winds is at least not dynamically important for young H2 regions or young massive star clusters, but they may be more important during the early formation. And then for just starting now, possibly the observed early low star formation efficiencies for GMCs is a combination between the initial turbulence, the magnetic pressure, and the stellar wind the radiation pressure feedback. And then finally, a complete picture requires more detailed simulations by including the prescriptions from other feedback mechanisms, so like from winds, radiation, and cosmic rays. Thank you.
Thank you. Do you have some time for questions? Anybody wants to ask questions?
Third line there.
Yeah.
Show that nice simulation where the star formation efficiency wasn't all that high.
Yeah.
But did you Did you run the equivalent non-magnetic case to see
Yeah.
what the previous equivalent?
I have not, and I want, the problem is, so we do refinement on the genes density, and so when I try to run that, because of the high densities, you get that the whole cloud will be refined. So yeah, the star formation rate will definitely go up by a lot. It just becomes very expensive to do.
You can always turn down the number of allowable results of refinement, just do a lower result version, if you want to make the direct comparison.
Yeah. Oh, yeah. So I mean, I could do the direct comparison because they don't have any refinement. Yeah. But we wanted to get better resolution with ours. You know, we wanted better resolution in magnetic fields and then also the direct radiation pressure. So I had to think more about, because like another thing I could do is I can mess with the genes number of what I want to refine on. But yeah, I've tried. I thought about doing it, and it was just like basically the whole cloud was refined to the finest level. So it became very, very expensive very quickly.
So then fields are very important, so you're saying.
Yeah. No, I need to look more into that because it would be nice to do the non-magnetic case. Yeah.
Well, I guess you can do a lower magnetic field case.
Yes, yeah. Oh, yeah, that's a good idea. See, yeah. Okay. Yeah, that's a really good idea. Like I can do like a mass to flux of 4 or something. Yeah.
Get rid of that word likely.
Likely. Oh.
The effects are likely.
Yeah. Well, I'm still running it.
So in these models of this energy sinks for the star clusters, you have these plots versus temperature. So you have some model density profile, and then you have as observational input, what infrared emission or what exactly is the observation?
Oh, so yeah, from this. Oh, yeah, I didn't show that plot before, but just paying attention to this one. Yeah, so that figure there is just kind of like the allowed plane. So
Right figure.
yeah, so this one, yeah. So so basically what I do is from the X-ray emission from these star clusters, or from the H2 region, I can calculate, if I assume a single temperature, single density hot gas that fills the entire H2 region, I know the emissivity of the gas, then I can calculate what the allowed number density is as a function of temperature. Yeah, and that's just straight from knowing the size of the H2 region and the X-ray observations. Yeah.
But then you have these different channels. How are you calculating these different channels?
Oh, yeah, I'm just considering the different energy. I'm calculating them directly. So I'm using like this for conduction, Spitzer formula for thermal conduction. For dust cooling, I assume a 1% dust to gas ratio.
But this is all versus temperature, so.
All the energy loss rates depend on temperature.
Yeah, so I mean, you're doing this in some sort of average sense? Or
Yeah. So I'm, yeah.
And so this temperature represents the sort of average temperature.
Yeah.
Gas.
We're assuming that the hot gas is at a single temperature and single number density. And then from that, if you know the temperature and the number density, then you can calculate the energy transfer rates for these different mechanisms.
Little dot.
Oh yeah, that's from that's from the observations. So like from the previous work by Lisa Townsley and like Laura Lopez, they give by looking at the X-ray emission, they estimate what the temperature is. So
That's where in this envelope you should actually set.
yeah, I mean it's all yeah. So that's why I put that there to kind of guide the eye more. But any of these along that line, along this line here, this shows the number density as a function of temperature. The hot gas can be anywhere along this line.
And so in the right curve, you principally be anywhere along that top parabola.
Here?
The right panel, sorry.
Oh yeah, no, this is just illustrating how much energy we're missing for a given temperature. Yeah.
Given the mean density.
Yeah.
Another good question.
You
Yeah.
mentioned in the beginning that the radiation pressure limit to mass to something like 30 to 40 solar masses, otherwise the ratio is up. So I was just looking at fragments, I'm curious. I mean, each fragments are much lower than 300 solar masses.
Oh, so in the previous, okay, so in the run, the star would have kept growing in mass. I just stopped running it because it got very expensive. So at the end, I'm left with the 40 solar mass star just for that run. But accretion hasn't stopped on the star. It just got very expensive because the majority of those bubble shells are refined mostly to the finest level. So it becomes too expensive to continue to run. There's a lot of fragments, and I think at the end of that run, there's about 70 solar masses total for the stellar mass, and so 40 for the most massive one, and then for the fragments, for the companions, it's about 30 solar masses.
So individually, they're not that massive.
No, and
In the end, it's going to merge for much more massive stellar?
potentially. I mean, so there's a lot of, so some of the problems with that is I don't have magnetic fields, so magnetic fields would reduce fragmentation. Another thing too is how we decide to create these particles. Our sync particle creation is pretty lenient compared to other methods, and also how we merge particles. So we only merge particles when when the lower mass one is less than like 0.05 solar masses, and that just corresponds to the fact that the star will be several hundred AU in size. Or like 10 or 20 AU in size, corresponding before to the first collapse. And so, yeah, so our multiplicity also depends on how we decide to merge particles. So it's hard for me to kind of give an answer about what it means for us. Another thing too is I found that the sync particle or the companions, number of companions, also depends on the radiative transfer treatment you use. So for example, I ran it also without the direct radiation, did it the old way, and I ended up with more massive companions and less fragmentation, and that's just because of the way that I'm dumping the energy leads to like puffier disks, hotter, puffier disks, so that's going to reduce fragmentation based on the gene's density. So there's a lot of factors. So one of the reasons why I didn't talk about the fragmentation at the end is because, yeah, I think a lot more work has to be done with that. It's very sensitive to the initial conditions, and to the algorithms you use and the initial conditions you use and so on.